Hi everybody, welcome to the lesson on normal distributions. I should say this is the first part of the lesson on normal distributions because we're going to spend 2 days on this section. And I'll tell you here at the outset that, that what we do in today's class is going to be really important. It's going to be the very basis of what we do in the next class and the class after that, and then it's going to come up a couple of times down the road again. So what we do today, you really need to get that down before we continue. So I really wanted to take today and concentrate on this part of it. All right, so before we talk about normal distributions, we need to talk about continuous distributions in general. And that's because the normal distribution is a continuous distribution. There are tons of other ones, but the normal distribution is one of them. So we need to talk about how to handle those first. So previously when we looked at discrete distributions, and I can scoot up here a little bit, we saw a table of values, right? We saw a bunch of x's listed and their corresponding probabilities. And to find those probabilities, all we had to do was, if you wanted, for this example, the probability that x equals 2, you just have to look on that table and see that's 0.37. Well, with continuous distributions, if you remember, a continuous random variable is one that can go out for many, many, many decimal places. In theory, infinitely many. And so what that means is that there are way too many values to list. If you had 200 observations in a data set, you would be likely to have 200 different values. So you can't list them all. So instead of listing them in a table like that, we show them in a formula or a graph. There are other implications of having a continuous random variable as well. The first one is that because there are so many possible values, infinitely many, as I said, the probability that you pick a given one of those is essentially zero. The analogy I've given in the past is if I took a grain of sand and put it on a beach somewhere on the earth, and I told you, why don't you go pick up a grain of sand somewhere on a beach, somewhere on the earth, there are infinitely many, basically, grains of sand, which means that the odds of you picking up the exact one I left behind is infinitesimal. It's essentially zero. So that's what we have going on here. There are so many possible values that the probability associated with any given one of those is zero. So instead of looking at individual values, we're going to look at intervals of values, such as the interval between -1 and 1, or the interval greater than 15, or the interval less than 102.5. And one nice thing, because the probability that x equals a given value is 0, for these examples, less than and less than or equal to mean the same thing. So now this is not true for discrete distributions, only continuous ones. If they ask less than or equal to, they're the same thing. Greater than or equal to, same thing. Okay, so you don't have to be careful about that. How do we find probabilities then? Well, the total area under the curve of any probability distribution is 1. So just think of it as, 100%. And I'll sketch something that might be a probability distribution. Let's say our probability distribution looks like this. Okay, so that one is skewed to the left. So the total area under this is 100%. Okay, that's this whole area in here. The probability of that 100%, if I wanted to find the probability between these two values, I'm going to sketch that area in between and find then what proportion of the total area is this shaded region. And that's what we're going to be doing. So area and probability mean the same thing. So if I ask the probability between these two values, that's the same as the area between these two values. And we'll see how to do those shortly. So now let's talk about normal distributions in general. The normal distribution is important to study because a lot of things fit the normal distribution. So it can be used to model a lot of real life things. It's also used as the basis for a ton of statistical inference. So there are a lot of things that either this is going on in the background, so some of the calculations are based on properties related to the normal distribution or the formula for the normal distribution, or a lot of times we need to be able to run some statistical procedures. We need to know that our data follows approximately a normal distribution. So the normal distribution looks like this. We've seen this before. Bell-shaped. It's symmetric around the population mean mu. It goes out for infinity in either direction. Let's see if this will let me draw in there. Theoretically. But it does get closer and closer and closer to this line here. So it's based on a mean. The mean is always in the middle. And the standard deviation tells how wide it is. The mean can be any real number, negative or positive or zero. Sigma, the population standard deviation, can be any real number as long as it's positive. It can't be zero and it can't be negative. So those are normal distributions in general. So these are normal distributions. I'm not trying to mark that out, I'm trying to circle that. So that's normal distributions in general. The one we're going to focus in on today is the standard normal distribution. Okay? So the difference between general normal distributions and the standard normal distribution is that the standard normal distribution is just one specific normal distribution. It just has a mean of 0 and a standard deviation of 1. Okay? Normal distributions in general can have any mean and any standard deviation greater than 0. But for the standard normal distribution, it's got a mean of 0 and a standard deviation of 1. For all the other normal distributions and just about every random variable, we'll call them x. But the standard normal random variable is called z. So whenever you see z, you can assume that's the standard normal. And whenever you're working with the standard normal, you do have to use that letter Z. Okay. Now, in case this is getting a little confusing, I wanted to break this down for you a little bit. So, overall, we've got continuous distributions, okay, as opposed to the discrete ones that we were looking at before. There are tons of continuous distributions. Normal distributions are some of those. So normal distribution is a particular kind of continuous distribution. And then the standard normal distribution is a particular normal distribution. Okay, so this is what we're looking at today, the standard normal distribution, and how to find probabilities based on it. So we said the normal distribution looks like a bell curve with the mean in the middle. Well, for the standard normal distribution, remember that the mean is 0, so 0 is going to go in the middle here. And we usually sketch values out 3 standard deviations in either direction from the mean. And so where the standard deviation is 1, that means we usually sketch from z of -3 to z of +3. But keep in mind that the distribution, as we said earlier, really keeps going. And we usually only stop sketching here because this line gets so close to the axis. Okay? So we're going to see this sketch over and over and over again. And we're going to be looking at, the proportion of the area under the whole curve that is between, say, 0 and 2, or you name it, any values in there. There is a formula for the normal distribution, and it's in your book. I'm not going to put it here because I don't want you to get the idea that I expect you to know it or memorize it. It's an evil formula. It's got the square root of 2 pi in it, and it's also got e in it. So it's a nasty formula. But it's not anything we can work with directly anyway. So we want to find standard normal probabilities. And it's really just a matter of knowing the function in Excel. So for example, if I want to find the probability that z is less than -2.35, I'm going to, and I want you to sketch your normal distribution on all of these problems. So 0's in the middle, and then we sketch 3 standard deviations below and 3 standard deviations above. If it's easier for you, rather than sketching, you can just copy this picture over and over again and draw right on it. That's totally fine. So we are looking for the probability that z is less than -2.35. So -2.35 on this number line down here is right about here. Okay. And I'm going to make some more room. So this is -2.35, and so we're looking for the area to the left. So I think you can see that's going to be a pretty small proportion of this total area. So the way this Excel function works, and the function is norm.s.dist. you have to tell it the value of z where you want the area to the left of it. Okay, so in this example, we're going to be using norm S dist negative 2.35. And there's a second argument there also, which is just always going to be true. You don't have to worry about that. I don't even know why they have that in there, because I don't think I've ever seen anybody use it where it wasn't true. So negative 2.35 and then true for cumulative. And we get a value of 0.00939. So this is probability z less than negative 2.35. So we get 0.0094. I'm going to go ahead and put this as true so you'll have it in your notes. So this tells us that this area here, this probability, is this area right here. So this is 0.0094. This means that if for some reason we had a set of values that followed this distribution and we picked one of them at random, the probability that it would be less than negative 2.35 would be 0.0094, so a little less than 1%. So let me tell you, this is to the way this function is written. You have to tell it the bound where the area is to the left of it. Why to the left? As my parents used to say, that's just how God made it. Or in this case, that's just how Bill Gates made it. That's just the way the thing is written. So if you want the area to the right, it means you have to do a little bit of finagling. Not a whole lot, just a little. I'm going to go ahead and, rather than sketch this every time, so if I want the area to the right of 1.86, 1.86 is between 1 and 2, but a little bit closer to 2. So I'm going to guess that's about 1.86. So I'm looking for the area to the right of that. So that's what I want. But if I type in norm S dist 1.86 true, it's going to give me the area to the left. In fact, let's see what that is. .86 true. That should be a large value before I hit enter. This is going to be a large value because that's giving me the area to the left of it. And so just as we suspected, or just as we knew, this probability is large, so 0.9686. And I am going to ask you to give me, to round to 4 decimal places. So for this one, for this first one, it would be 0.0094, not just 0.0093, because we're not truncating, we're actually rounding. Anyways, so this gives us the area to the left. If we want the area to the right, keep in mind that this whole thing together is 1, which means that these are opposites of each other. So if I want to find, let's see, they said this was 0.9686, I believe. Yeah. This part is 0.9686. I'll sketch it in red. So that's all of this. But the whole thing together is 1. So if we want to find this shaded area, the black one, we just have to do 1 minus that. So if we do 1 minus 0.9686, that gives us the area to the right. And that's because it's basically the same thing as, you know, if I told you there was a 96.86% chance that it rains tomorrow and asked you the chance that it doesn't rain, you just do 100% minus 96.86%. So it's the same thing as that. So I would recommend that instead of doing this in 2 separate tables, in 2 separate cells, that you just put your 1 minus here in the front. So if you do 1 minus norm S dist 1.86 true, that will give you the area to the right. Okay. Now, this is probably spoon feeding on my part. So if you want the area to the right, in other words, greater than, it will always work to do 1 minus norm S dist. Okay. If you want the area to the left, it will always work to do just norm S dist by itself. There's one more scenario, and that is between. So if I want to find the area between negative 1.4 and 2.3, let me sketch this here. So negative 1.4 is right about here. And 2.3 is right about here. We're looking for this area in between. Okay. Now, we only have the less than at our disposal. That's all we have. I'm going to see how clever I can be with the sketches. Well, I'll just draw this one. Here's what we're going to do. We're going to find this top area, and then we're going to subtract the bottom one. So in other words, 2.3 is there. We're going to find this area. So this area minus this is negative 1.4. This area. So if we take this large area and subtract the small area, we'll be left with what's in between. So to find this one, this is norm S dist 2.3, true, minus, and this one is going to be norm S dist negative 1.4, true. Okay. Let's first do that in pieces so you can get a better idea of how this is working. So let's do this first part. So norm S dist 2.3 true. So 0.9893. So this area here is 0.9893. Now I need to find this area here, or this area here, which is that formula. So norm S dist negative 1.4 true. And that small area is 0.0808. So this area here is 0.0808. And all we have to do now is subtract them. So equals the big area minus the small area, and we get 0.9085. Now I would put this directly in. I wouldn't, while you're learning this, it's okay, but I think it might even be easier, even now, to just type it in directly as the norm S dist minus norm S dist. So I would do it as norm S dist. What was that top value we had? Yeah, I know. It was 2.3 true minus norm S dist 1.4. That was negative 1.4 true. And we get our value here. And so if you want an area in between, so this was probability negative 1.4 less than z less than, I've already forgotten what that value was, 2.3. So if you want an area in between two values, you can always do norm S dist of the larger value, and I mean the one to the right, minus norm S dist of the smaller value. Okay, and that will always work. So just to review, there are, here in this part, what we're doing is we are, just want to point to one of these because I'm a math teacher and I can't talk without pointing to something. We are given a range of z values, like z greater than 1.86, or z between negative 1.4 and 2.3, or z less than whatever we said was up here, negative 2.35. So we were given a range of z values, which is, it looks like that, and we were asked to find the probability. Okay? And to do that, we needed to find the area under the curve corresponding to that range of z values. There were 3 scenarios. There was a less than scenario, where all you have to do is type in the norm S dist of the value you're given, of the edge of this boundary. There was the greater than scenario, where you need to do 1 minus norm S dist, that boundary. And then there was the between scenario, where you have to do norm S dist of the upper value minus norm S dist of the lower value. All right? So that's it for this section, or for this part of this section. Stay tuned for the next part.